Both arrays and lists are collections, and I'm using the word collections in its most general sense, that arrays and lists are both ways to group multiple items together under one name, whether those items are integers or strings or custom objects. But the biggest difference between a simple array versus a simple list is in the idea of direct access versus sequential access, and this is all to do with the way that these data structures are stored in memory. Here's what I mean. If we have a simple array, it's typically allocated in a contiguous area of memory. All the elements, whatever they are, integers or doubles or references to objects, they are next to each other. And because of the predictability of this structure, we can go directly to any specific element just using the index. And it doesn't matter how big the array is. We can jump directly to position 10,000 just as easily as getting to position 0. Any element can be accessed as easily and quickly as any other element. We don't need to work our way through the entire array unless we're doing something like a linear search, and this is what I mean by arrays support direct access to the individual elements. Sidebar: direct access is also sometimes called random access. I've never been a fan of this term, as random access seems to suggest we have no control over where we're going. We're just shaking the magic 8-ball and getting some random element. That's not what random access means, but when you see this term applied to a data structure, just think direct access. We can get to a specific element directly without having to work our way forwards or backwards through the entire collection. Sidebar over, that's arrays, so what about lists? The classic distinction is that if arrays are about direct access, then lists are about sequential access. That a list is a collection of multiple elements, but its structure is not based on a strict numeric index like an array is. Instead, the list keeps track of a sequence of elements. Might be 5 elements in your list, might be 10, might be 1,000, but these elements, whatever they are, could be stored anywhere in memory. They do not need to be located next to each other the way that an array is typically allocated. Well, that just sounds like a bunch of separate objects, you might think, but wait, we're not done. See, unlike an array, a list doesn't have a numeric index, that's true. Instead, when you access the list, what you get is the first element, sometimes called the first node of the list. And a list node is a very simple wrapper object, often something as basic as a struct, that holds your element, your value, whatever object that is, and also contains a link to the next node, the second node. In languages like Java and C#, this link would be an object reference. In C or C++, it would be a pointer, but you get some kind of reference to the next node. So when we read the first element, the first node of the list, we use that link to get us to the second node, wherever that's located in memory. We get the value of it, and the second node also has a link to the third node, and so on until we get to the final node in the list. We reach a node that goes no further. Either the link to the next node is null, or it might link to what's called a terminator or sentinel node. And a sentinel node is really just a dummy node, a dummy object that doesn't contain any element value. It's just there to indicate in no uncertain terms you have now reached the end of the list. So this is the idea of a list. More specifically, this is the concept of what's called a linked list. This is still ordered data. There is a specific sequence of nodes where each node is containing some kind of value, but also contains a link to the next node. Now, the big difference, number one, the biggest downside of a classic linked list like this is we have to access the elements sequentially. Because of the way this is built, we cannot jump directly to element number 5 or 10 or 1,000 without beginning at the first node and working our way through, following all the links from one to the next, to the next, to the next. And this is sequential access. And you might think, well, hang on a second, Simon. See, I know I can also do sequential access with a regular array. After all, we could do a for loop or a for each and iterate through the entire array, just increasing the index one by one. So if arrays give us both direct access and sequential access, well, why would I ever pick this list thing that limits me to sequential access? Good question, imaginary viewer, and here's why. The big difference number 2, the enormous advantage of a linked list. Because of the way it's built, adding and removing elements is much, much easier than with an array. See, in an array, where the items are taking up contiguous space in memory, as we've already seen, if I want to insert a new item at position 2, It requires all the other items to be shuffled around so it can keep its meaningful ordered structure. And this can be very demanding, and it gets worse and worse to reshuffle items as your arrays get larger. Even adding elements right at the end, although it's easier in an array, it can still require reallocation of the entire array in order to always keep a contiguous area of memory. To add a new node at the start of this list, I would just create that new node wherever we have space in memory. I would point the list to it and tell it it's the first node, and point it to the previous first node. Everything is still now in sequence. It's done, but no other nodes needed to be changed or shuffled around. Same at the end. If I want to create a new node at the end, I build that new node, I point it to the terminator, and I point the previous last node to it, and we're done. Even deleting a node, even from the middle of a list, is also simple. If I wanted to remove object 3 here over on the right-hand side, well, it just requires that the previous node, object 2, that's currently pointing to object 3, changes its link to now point to object 4. We've then effectively taken a node out of the sequence. We can just go ahead and get rid of object 3, and all the other nodes in the list, whether that was 5 or 5,000 or 500,000, are completely untouched. So if you have very volatile, changeable data, the difference here can be huge because we don't need to rearrange existing elements. Adding elements to a linked list always takes the same amount of time, whether the list is small or the list is large. It is a fixed time process. But adding or removing elements in an array gets more and more inefficient the bigger the array gets. So our central challenge as we understand our data and what we need to do with it is that arrays are really good at direct indexing and bad at adding and removing elements. And lists are really good at adding and removing elements and bad at direct indexing. Neither of these are good if you have to do a full linear search, although arrays are easier to sort and do a binary search if that's an option for you. And we're going to talk about the support for these ideas in various languages in just a moment, but we're not quite done yet, because we've talked about a linked list, but there's more than one kind of linked list. Let's see that next.